Hello guys, this is Matthew, and today I thought that I would just make a quick video to kind of explain a little bit about the output of certain different kinds of motors and why certain motors will output AC and why other motors will put out DC, unsmooth DC but DC. So for this first example, I just wanted to show you this is a brushed DC motor. And a good rule of thumb to think about is that if a motor can accept direct current, it will put out direct current if it's being used as a generator. So if we turn on the drill, you can see if I move this, you can see it move a little bit on the screen there. If we turn on the drill, before that, let me just real quick explain how I have my oscilloscope set up. It's in DC coupling mode on channel 1 here, and its time base is really short. This isn't a memory oscilloscope, so unfortunately we just kind of have to deal with the strobe effect if we want to see the noise on this. But essentially, this middle line, oops, wrong dial. Oh, you son of a diddly. Here we go. So this middle dial here, I've positioned it right in the middle of the reticle, and that is 0 volts. So if we have an AC sine wave, we should see it coming up and down both in the positive and the negative, and that would be our AC current. I've got this connected to a drill. I don't have one with a gearbox on it, so this isn't going to be the best in the world, but just watch the oscilloscope, the screen of the oscilloscope. Now you can see that it's a really crusty looking signal, but all of the voltage that was generated up here. We don't have anything going over this crossing line here. And that is on a brushed DC motor. Now if we were to do the same thing on a brushless DC motor, we would see a great deal different on the screen. The same goes with if we were to use a stepper motor. It also would display what is essentially sine waves on the screen. It definitely wouldn't display this crusty looking signal up there. And you'll notice if I reverse the spin, it goes low. So what's going on with this? Well, to explain this better, let's just go to Notepad, and I will kind of draw it out and explain what's happening. Okay guys, so I've just drawn this out, this demonstration here, just kind of to try to help make sense of this a little bit. And for this demonstration, I just kind of have this simplified down pretty good. We'll first talk about the construction of motors, of permanent magnet DC motors in particular, or brushed DC motors. Essentially, you have an outer ring made of a magnetic material, like ferromagnetic material. So, and it'll have inside the material, it'll be set to where there's alternating poles. It's like north south, you know, kind of around like that. And on the rotor, you will have sets of coils. We'll call this coil A, and we'll call this coil B. Now, when a voltage is applied, well, actually, let's treat this like a generator. That would make more sense for what I drew out here. When you spin the rotor, this coil here, this coil set, so coil A, will pass north pole, then it'll pass the south pole, it'll pass north, and it'll just keep doing that around over and over. When that happens, you generate an AC waveform because suddenly, current's flowing one direction, and then it'll start to flow back the other direction, and that's where you end up with this nice sinusoidal AC waveform. But that is on coil set A. Now coil set B will be the exact same thing, except in this demonstration, because it's like 180 degrees out of phase, or 90 degrees out of phase actually. Well, wait, sorry. Anyways, because it's completely parallel to this, you'll end up getting the exact same nice waveform, except it'll be pointing in the opposite direction. If you were to be able to probe both of these, each one of these coils, then you would see it changing, but in exactly opposite to coil A. Now, if you were to probe and be able to look at both coils, you would end up with something like this. This kind of falling and joining set of AC waveforms. You'd end up with something like that. Now, this is exactly this. Well, actually, before we go there, let's talk about. So now that we've seen that, and that we are generating AC on each coil, if we do that with 3 coils, we end up with this. And if you know, and this is basically a 3-phase type of power. You've got 3 different phases, and they're all, out of phase with each other. And you always have a positive voltage generated, and you always have a negative voltage generated. And this is very much so like the brushed DC motor that we just looked at. Now, what makes the reason why we're not seeing all of these different waves, though, is that as the rotor moves, so does the commutator bars that are attached to the rotor. And as things switch over, as you switch over between coil sets, you're cutting off the rest of the sine wave before you actually get to observe it. So like the output going across the wires is cutting off a lot of what's actually happening inside the motor. So if we take this ruler in here and we just look at one coil, we'll look at coil A. Once it hits kind of a halfway point, we'll go back to the 2-pole example to make it easier. Once it gets to like the halfway point, it's going to cut over and to coil B, the commutators are, and the brushes. At that point, you're going to see the top of this waveform. So first you'll see the top of this, then you'll see the top of that, and then you'll see the top of this, and it'll just keep alternating back and forth like that, so that you never have on one wire, you'll never have on the positive wire the voltage dip negative, and vice versa. And that's where you would get this kind of waveform. Since we do have multiple, sets of coils, say 3 coils, and thus we have 3 sets of commutators, we're never seeing all of this sine wave nonsense happening either. We're actually seeing just the top. So like if you think of it cutting off at every crossing point here, which is really what it's doing, well, if I could draw sine waves, then you would be left with just the tops, just the humps. And that is what we observed on our oscilloscope. And so essentially what's happening is that we are physically rectifying our AC waves. In particular, we're physically rectifying a 3-phase wave system and only getting a DC voltage out. Now, it's not perfect
So you'd get something that's much dirtier looking than just this, hump, hump, hump. Uh, but that's the kind of the principle as to why this is happening. And it's important to understand that even though this is extremely choppy, because of the commutators, even this would be considered just unsmoothed DC, an unsmoothed DC waveform. The reason why is because, again, the positive wire and the negative wire will always stay in the same polarity. So the output will always be in the same polarity. And you'll never have a DC voltage on something. And as a result, you'll never have an AC voltage on any one of the wires. And as a result, you could put a sufficient capacitor across this ugly waveform, and you would end up with a perfectly smooth, proper DC waveform. Now, if we were talking about a brushless DC motor, however, the roles would kind of be reversed. You'd end up having these windings on the outside and the magnet with the different polarities on the inside, and then that would spin, and then that would allow you to actually observe all of these waveforms. You would have, for a three coil system, you would have 3 separate sets of sine waves, and you can actually view that if you take a brushless DC motor like you would see for a quadcopter, say, and spin it with a drill. You'll actually be able to see 3 separate sine waves. I don't have one of those though, so I can't really show you. And the only stepper motor I found is basically it's dead, so I couldn't. It was already kind of torn apart. So, anyways, so that's kind of the explanation as to why we're getting DC voltage. As it applies directly to the video, the hand crank flashlight video that Diode Gone Wild did, based on the using an old CD drive tray to do that with the gears and everything. The reason why, when he spun the drill in one direction, one LED lit, and then spun it in the other direction, the other LED lit, was because you are physically, the commutators are still cutting things off in the same place. But since you're spinning things in the opposite direction, you are actually you're going to always see just the negative across the positive wire, or depending on which way you switch it. But you'll still end up seeing just the tops of a sine wave. And then that's how you'll end up generating that DC voltage in 2 separate polarities. And that's why when he stuck the 2 LEDs together in like anti-parallel, the legs, and he spun it one direction, it would light in one direction. Then if you spun it the other direction, it would light the other LED. So yeah, I hope that this explanation helped clear up some of the mystery behind why both of those LEDs weren't lit up together. So yeah, if you guys like this video, just let me know. If I said something wrong, also let me know. I'm always up to learn more. So thank you very much. I'll talk to you guys later.